Hello, thank you for joining us today. I'm Suzanne Staggs, the director of ACT, and I'd like to start this by thanking the many members of the ACT collaboration who've helped make possible the work that's going to be described today. But also just huge thanks to the NSF. They've supported the CMB for many decades and ACT directly for more than 20 years. The first NSF award to ACT let us build this brand new, huge microwave telescope in the Chilean desert. And we outfitted it with a type of detector that at the time hadn't even been fully demonstrated, the TES bolometer. And then subsequent NSF funding let us add polarization sensitivity to ACT with this ambitious receiver based on a dilution refrigerator. And the receiver was quite successful despite the difficulties you might imagine can exist with a remote and high altitude site. And then a third NSF award let us incorporate these remarkably really sensitive large format TES bolometer arrays from NIST into an even more powerful camera, and also let us undertake these huge maps that we're going to be talking about today. So thank you for coming and for your time. And Joe Dunkley, the analysis leader of ACT, will now introduce the main themes and speakers for today.
Thanks, Suzanne. So we're delighted to present work from 3 new papers out today by the ACT collaboration. This is part of a series of papers from ACT Data Release 6. The first one, shown at the top, is with the lead authors, are new maps of the cosmic microwave background, half sky, beautiful maps that you'll see of the intensity and the polarization of the cosmic microwave background. And you'll hear from Sigurd Ness and Adri Diven-Vorden on these and also our data release. We then take those maps and look at their power spectra and describe those properties and investigate how well the Lambda CDM model still does with our data. And that will be Thibaut Louis, Hida Jense, and Adrian Laposta presenting. The third paper is Constraints on Extended Cosmological Models, and you'll hear from Amelia Calabrese and Colin Hill on a whole array of investigations that we did into different physical models. Mark Devlin will wrap up with Q&A. You can put Q&As into Q&A, and we'll be gathering them and answering questions at the end. The papers should be on our website by the end of this webinar and on the archive tonight. And I can also point you to Zach Atkins' talk at APS tomorrow in APR P21 session. We have also a follow-up webinar next Monday to describe our data products and notebooks better. So with that, I'll be delighted to hand over to Sigurd Ness, who's going to be telling us about the maps.
Okay, so I'll just start by introducing the telescope. So the Atacama Cosmology Telescope was a 6-meter CMB telescope that observed from 2007 to 2022 at a site at 5,200 meter altitude in the Atacama Desert, which is shown with this pink dot here in South America. There's a zoom on the site in the lower right here where you can see ACT itself surrounded by its big ground screen, together with some other telescopes nearby. For example, the big ALMA array down on the plain there, and our neighbors CLASS and Polar Bear, as well as the not yet built at the time of this photograph, Simon's Observatory and CCAT Prime up on the mountain. So there are only a few places in the world that are suitable for CMB observations because water vapor gets in the way. So you want a really high, really dry location. And this location in the Atacama Desert is maybe the best one in the world for sky coverage because it's relatively near the equator, and the second best for weather after Antarctica. So what we'll be presenting today is the data release 6 data, which covers the 2017 to 2022 period. And of this, we have 828 full days of CMB observations, which works out to around 44% observing efficiency. And of this, the nighttime half makes up our primary data set that most of our results will be based on. Here's a bit of a closer look. In the lower left, you can see the telescope again with the 6-meter primary mirror and the ground screen. And on the right, you can see a zoom in on the receiver. And you can see that it consists of these three parts, the three detector arrays. And for DR6, these were PA4, PA5, and PA6, which observe in three broad bands, centered on roughly 95 gigahertz, 150 gigahertz, and 220 gigahertz, which we label F90, F150, and F220. And together, we have around 3,750 working detectors here, which work out to around 70% yield, which observe at 100 millikelvin temperature. And when combining all of these bands together, the combined sensitivity is around 6.2 microkelvin root second. And our beam size in the F150 band, the middle of these bands, is around 1.4 arc minutes full width half maximum. So for DR6, we went for a quite large sky area. So you can see this here in yellow. So we cover around 45% of the sky, and we have a large overlap with other surveys, some of which are shown here. For example, there's Euclid with the blue contours, Hyperse PrimeCam in magenta, SDSS and DESI in green, DES, Dark Energy Survey, in red, KIDS in light blue, and many others. For example, LSST covers almost the same area as ours, just filling in that missing part down here. We also have a large improvement in depth compared to our previous data releases. There's the previous full data release, DR4, and previous interim data release, DR5. And you can see those compared to DR6 in the plots below. So the way to understand these plots is that we're showing the depth in the maps in microkelvin arc minute units. And you can imagine that we've taken all the pixels in the map and sorted them by their depth. So the deepest pixels are on the left and the shallowest pixels on the right. So this is basically showing the distribution in depth. Intensity on the left and polarization on the right. And you can see in red, there's the DR4, in blue, DR5, and in yellow, DR6. The dashed curves are night-only data, so the primary data set, while the solid ones are if you also include daytime data. And you can see how big an improvement we made here from DR4 to DR5 and to DR6 now. You can also see that we're improving over Planck by quite a bit. So what you have here in the gray dashed curve is all the Planck frequencies co-added. And you can see that we are deeper than Planck over around 19,000 square degrees on the sky. And our typical average depth is around 1/3 the white noise RMS of Planck. And our improvement is even bigger in polarization, where Planck is not quite as sensitive as the square root of 2 factor you'd expect. Okay, but what do the actual maps look like? Well, to set the stage, let's start by looking at the sky as Planck sees it. So this is the Planck F150 total intensity sky. So you can see the CMB blobs in the background here, and you can see a few spots where there might be some other objects. Now, let's switch, or rather add in the ACT DR6 data. So I'll go backwards and forwards a few times, and you can hopefully see that not only does the CMB sharpen up and the noise goes down, but you can also see that all the smaller details suddenly appear. So you can see suddenly there's a spiral galaxy here. There's a bunch of active galactic nuclei in red, and you can see a few galaxy clusters showing up in blue here. But of course, we don't just have a single frequency band. We have 3 of them in DR6, and so we can map the F90 band to the red color channel, the F150 band to the green color channel, and the F220 band to the blue color channel. And that results in an image like this. So, of course, the CMB still looks gray because in these units, it's got the same intensity in all the bands, but you can see everything else suddenly shows up with color. So You can see now that this spiral galaxy shows up in blue due to its dust, and suddenly it's also apparent that there's another spiral galaxy up here. The active galactic nuclei show up in red due to the synchrotron radiation, and the clusters show up in dark blue. So I've highlighted these objects here. We can also filter away as much of the CMB as we can just to see how many of these objects we have. So this is showing the same size here of the sky, though it's a different patch, so you can't see that spiral galaxy anymore. But you can just see how many of these are. It's basically like a starry sky with all these objects. So we see around 30,000 of these objects, active galactic nuclei in our patch, and between 6,000 and 10,000 of these galaxy clusters, depending on how you count it. Okay, so that's total intensity, but what about polarization? After all, much of our constraining power comes from polarization. So again, let's start with a Planck-only map. So this is what Planck sees in polarization. So you can see that there is, you can clearly see something going on here, but it's mostly noise. It's quite hard to pick up the signal. But if we add in the ACT DR6 data, we get this instead. So hopefully it's quite clear that we have much higher signal to noise in polarization than Planck. So all of these little blobs you see here is the real CMB E mode signal in this area. And we have this over basically the whole sky. So this is the full area, ACT plus Planck, and you can see, well, it might be a bit hard to see zoomed out this much, but basically we have these high signal to noise E modes over the whole area. Okay, but there are some caveats with these maps too. So first of all, when I talk about the depth we have and compare it to Planck, we only reach our full sensitivity on small scales. So this plot shows the noise spectrum. So the higher on the y-axis, the more noisy one is. And it shows the length scale or the multiple on the x-axis. So on the right here, we have the smallest scales, and on the left, we have the biggest scales. So the full depth is what we reach here in the noise floor, where the graph is flat. Well, if we go to larger scale from that, you can see the noise starts rising due to the atmosphere. Of course, that's a much smaller effect in polarization than in total intensity because the atmosphere is unpolarized. Okay, another thing is that we have some azimuth synchronous pickup that manifests as horizontal stripes in the map. So what you can see here is a raw map in total intensity and Q polarization. And in both of them, you can see some horizontal stripes. They look particularly worrisome in Q polarization and U polarization, not shown here. But it turns out not to be as big a deal because almost all of this signal is constrained to multiples M, as in ALM, the M there, less than 5. So if I remove only those few modes, you go to this. So basically, this pickup makes up a tiny, tiny, tiny part of the maps. So after removing those, you're basically left with those stripes. And what remains, the large scale stuff here you can see is just correlated noise from small part of the atmosphere leaking through. Two other things is that on the largest scales, especially in total intensity, we have a signal deficit for multiples less than around 1,000, which are caused by data mismodeling. So this is mostly a sub% effect, except if we go below L of 400, where it becomes a bit bigger. Also, in the same multiple range, there is some intensity to polarization leakage for partially the same reason. More on those later. Okay, so we make the maps available as a primary data product in ACT DR6, and you can find them on LAMBDA. They are also viewable as a data set in the Aladdin Sky Atlas. There's a link to an example one there, but you can find them, or you will be able to find them by default in the main desktop version of Aladdin. And we also have a web atlas where you can pan and zoom around and switch and compare to other maps, though sadly it's not compatible with Safari. Okay, and with that, I'll hand over to Adri Duvenborden.
All right. Thank you, Sigrid. Can you go to the next slide? Great. So yes, so one of the most basic forms of calibration that we have to perform is the calibration of the beam, or the point spread function, which really just quantifies the response of our instrument to the sky as function of angular scale. So we do this using hundreds of observations of Saturn and Uranus, as well as the quasars that appear as point sources in our map. Here at the bottom, you can see an example of these observations. These are just stacked observations of Uranus, and they clearly reveal the beam shape. On the right, sorry, can you move back one slide? Sorry, on the right, you then see how this information makes it into our cosmological analysis. This quantity B that describes as function of multiple L the response of the instrument to the sky. And here you can see that ACT has a pretty high resolution. Like Sigrid said, it's like 1 to 2 arc minutes roughly. Next slide, please. So if we take a look at these planet observations in polarization, we see a faint signal appear. And this signal is not due to the planets themselves, but it's due to the telescope, and also partly due to some non-idealities in the data reduction. Here at the bottom left, you can see 2 examples for 2 of our arrays of this type of temperature to polarization leakage. So it turns out if we ignore this leakage and we compare our different detector arrays in consistency tests or null tests, we find that in our TE null tests, there are biases that are clearly detectable. However, if we use the planet observations and predict the leakage that we would think there is, we find that we pass these null tests. Our arrays become consistent again. Here on the right, you see a similar beam plot as I showed on the previous slide, but now one that describes the leakage from the temperature anisotropies to the E-mode polarization as function of multiple. And it's important to see here that the leakage for our different arrays, there are 4 depicted here, has a different sign. So that means that when we compare the different arrays, this leakage doesn't cancel. So these tests have been very useful for us to provide trust that this leakage model is good enough to describe our data. Next slide, please. So the final beam-related thing I wanted to mention is that because of our high sensitivity, we now have to take into account the fact that the beam has a frequency dependence on its own, as depicted here on the right. So in practice, this means that for every sky component, we use a slightly different beam that's determined from the spectrum of the source on the sky and its interplay with our instrument. In the past, this effect has been oftentimes ignored, and it turns out that for the main cosmological parameters, this indeed is a small effect. We see hardly any change by including this effect. But if we look at the parameters that govern the foregrounds in our data, we do see significant shifts. For example, if you look at the parameters that determine the thermal Swing-Absalon-Fichte effect. And then the final slide will be, the data release, as Sigrid briefly mentioned already. So we release our data on these 2 platforms. First, the LAMBDA Legacy Archive, where we put our raw maps, our processed maps, as well as our MCMC chains and the power spectra. And then the second platform is the CMB data directory on NERSC, where we put, in addition to all the products that were on LAMBDA, we put a special set of short exposure maps that you can use for time domain analyses, noise simulations, and the entire set of products that you need to reproduce the power spectra that you will see in a minute. We would really like to thank the groups that are in charge of the Lambda Legacy Archive and the NERSC directory for their help with making this quite large data set public. And then finally, we make available on our GitHub page a set of IPython notebooks that serve as tutorials to help you interact with that data and reproduce certain types of analyses. So then we move on to Thibaut Louis, who will talk about the power spectrum.
Thanks a lot, Adri. Next slide. So in addition to the data release, we believe it's the first time in the field, are going to release the entire analysis pipeline that will allow you to go from the public product, so the map on the beam, to the cosmological parameter result. So the pipeline includes power spectrum covariance matrices estimation, temperature to polarization leakage that Adri just mentioned, correction. Also a completely separated pipeline that allow you to cross-correlate the ACT DR6 data with Planck. And this was very useful for us at different steps of the analysis. But we are also, of course, also releasing a likelihood function for cosmological parameter estimation. So all of this goes to the public domain. Next slide. So Sigurd already mentioned the noise property of the data, but a very good summary statistic for the noise property is represented at the bottom of this slide with the effective noise power spectra. So in dark blue, you see the effective noise power spectrum of Planck, and in red, you see the one of ACT. And when the noise power spectrum is below the signal curve, which is represented in gray here, it means that we are signal dominated. And you can see that this is the case for multiple up to L equal 1500. So this corresponds roughly to 0.1 degree, which means that the map that Sigurd showed you at the beginning of the talk is signal dominated for all of its features which are bigger than 0.1 degree. And this is why they are looking so beautiful. Another thing that you can see from this slide is that the different array bands that we are using in ACT have comparable constraining power. They are the different PAs that you can see here on this figure. And this was very useful because it means we have a lot of redundancy in our dataset, and it was very useful for testing the dataset. Next slide. And indeed, we did a lot of tests. We actually did around like 2,000 null tests on the data. We checked that the results do not depend on array bands, weather condition, scan elevation, sky location, time of observation. We even tested that it does not depend on the position of the detector in the focal plane. If you look on the right here, you will see one of our most constraining tests, which is comparing the signal seen by different cross-frequency power spectra. So 90 cross 90 with 150 cross 150, for example. Of course, when you are doing this comparison, you want to correct for the foreground. But our null hypothesis is that after correcting for the foreground, they should see the same CMB sky. And here you can see the PT, so the probability to exceed for this null hypothesis. And you can see that our different frequency channel see the same CMB sky. Next slide. Now I think it's time to dive to the result, but just before that, I would like to remind everyone of this beautiful measurement from the Planck satellite of the temperature power spectrum, depicted by the orange point here. And now let's look at the DR6 data. Next slide. Here you can see the temperature measurement from the ACT DR6 data. So you can see different things on this plot. The first thing is that the DR6 data extend Planck measurement to small angular scale, corresponding to large multiple here. But you can also see that we are actually very consistent with Planck on overlapping angular scale. And the last thing that you don't is that I did not mention here, but that you can see with your eyes here is that there is actually a common model that is fitting both Planck and ACT, and it's given by this gray curve here. I'm not going to reveal you what the gray curve is. We are going to reveal it at the end of the webinar. Next slide. Okay, this is probably where we have the most impact. So this is the E power spectrum as measured by Planck. And if you go to the next slide, you will see what we are adding to the top of this with ACT. And here you can see that not only we are improving on small angular scale, but that even on intermediate angular scale, so around L greater than 600, we are actually very competitive or better than the Planck measurement. So this is really one of the most beautiful results that we are going to show you today is this measurement of the E-mode power spectrum with very minuscule error bar. You know, you can see all the peak in them. And this has actually a lot of constraining power, in particular when you are going to try to constrain extension to the lambda CDM model. Next slide. And finally, let's look at the T power spectrum, so the correlation between temperature anisotropy and E-mode anisotropy. This was measured by Planck. Next slide. And this is what we get when we are adding the ACT DR6 on the top of it. And here you can see all the wiggle and all the peaks, which are like super well resolved with a combination of Planck and DR6 data. And actually, this observable by itself place very stringent constraints on the cosmological model. So for example, our H0 measurement, just from this spectrum, ignoring all of the other, is of order 1.1%. And this is important because this spectrum is very not affected by foreground, for example. So it allows us to do very clean cosmology just from this single probe. And now I think it's time to discuss the gray curve. So I will pass it to Ida.
Thank you very much, Thibaut. So at this point, I'll talk about the likelihood software. So we are receiving these multiple multi-frequency cross spectra, and our likelihood software is going to model for a bunch of various sources of both galactic and extragalactic microwave emission that we need to account for. So here on the left, we have a figure where we show our data in the blue points and our foreground model in the form of a variety of components in these colored curves. In the top left corner at low frequencies, you can see this red curve. Those are point sources that dominate in the foregrounds at small angular scales. And if you go to the lower right, there at higher frequencies, you see a different curve. This is cosmic infrared background, and galactic dust tends to dominate at these frequencies. So we use MF-like, which is a multi-frequency likelihood software being developed by the Simons Observatory collaboration as our baseline likelihood model to really produce our ACT-based results. Most of this modeling is the same as in previous ACT releases. The main differences are that we do a full bandpass uncertainty treatment in this new likelihood model that's not been done before by us. And we've also found that with our new improved data, there's some evidence for a steeper thermal Sunyaev-Sadovich power spectrum. This is what I showed at the right here, at very high significance. And this steeper power spectrum, which we characterize with this alpha TSZ parameter, is in good agreement with n-body simulations with an enhanced baryonic feedback. If you go to the next slide, please. In addition to the multi-frequency likelihood, we also release an ACT-light likelihood, which is a compressed likelihood for fast cosmological exploitation. Here we have pre-marginalized over all the foreground contamination, as well as most of the instrumental properties of ACT, releasing a CMB-only signal between Ls of 600 and 6,500. This is what's shown on the right here. You'll note that in temperature, because of high foreground contamination, these data points are highly correlated. But as you were saying, in polarization and temperature polarization cross spectra, there's very little foreground contamination. So these data points are very uncorrelated with each other. These two likelihoods, although they are different, they agree very well with less than 0.1 sigma differences in both lambda CDM and extended models. If you go to the next slide, please. With both these likelihoods, we are presenting results in a variety of data combinations. We are presenting you as the ACT results. And when we say ACT, we mean the primary CMB measured only from ACT with a minimal contribution from the large scale EE modes from Planck to measure the optical depth at reionization. In addition, we combine ACT with several large angular scale primary CMB measurements from Planck PR3. We call this the P-ACT combination, or from WMAP in our W-ACT combination. And on top of those CMB observations, we also add lensing from ACT DR6 and Planck, BAO features from the DESI year 1 dataset, and supernovae from the Pantheon Plus supernovae sample. And these are in combinations that we will refer to as LB or LBS. If you go to the next slide, please. I'll now hand it to Adrian Laposta, who is going to talk to us about the lambda CDM constraints from ACT DR6.
Thanks a lot, Ide. Indeed, it is now time to look at what DR6 can tell about cosmology and the lambda CDM model. And in particular, I will jump straight to the result to give you the feeling that we had when unblinding the parameters. So here are the constraints that you can see on the right. So these are posterior distributions for the main lambda CDM parameters that we are able to constrain with the ACT dataset that are the expansion rate of the universe, baryon and cold dark matter densities, and the primordial scalar index. And the first thing that you see here on this figure is that the two data sets seems to be very consistent. And indeed, when we quantify the difference in the 4-dimensional parameter space between the two, we found that they agree well within 1.6 sigma. But the fact that they agree and that the contours overlap means that we might be able to find a common model that fits both data set. And this is the gray model that Thibaut mentioned before. And if we go to the next slide, you can have a look at the bottom left panel here, which shows the interplay between the ACT and Planck dataset to break degeneracies in parameter space and provide improved constraint from CMB data on the lambda CDM model shown as the dark blue contours here, the p-ACT contours. And from this combined dataset, we can derive best fit theory predictions for the power spectra, and you can see one of these prediction as the gray line on the right-hand side of this slide, compared to ACT and Planck measured EE bond powers. And as you can see on this plot, mainly if you look at the residual at the bottom of the figure, you can see that basically this model is a very good fit to the data on a wide range of multiple, and in particular, the scatter here, if you look at the scatter of the points, it's of order of few microkelvin squared, so which is a good indication that this is a good fit. We further quantified the goodness of fit of this particular constraint by computing the chi-square of ACT data alone or the full combo, and they respectively have a PT of 63 and 81% for these data sets. Of course, here I showed only the EE power spectrum, but if I flip between these slides and the two next slides, you can find the TE power spectrum here along with the residual and the TT power spectrum as well on the next slide. And the same conclusions holds for all of them. So you can go to the next slide for the TT power spectrum. Yes. So yeah, the residuals looks also good. And a further test that we can do about that is to break down the p-ACT dataset into contribution from TT, TE, and EE. And on the next slide, I show the constraints coming from these sub-datasets, so the p-ACT breakdown datasets, for which I'll show some of the contours here. And they are all in very good agreement. They seem to overlap, and they also agree with the combined p-ACT constraint depicted as the dashed black line here. Next slide. And if we want to provide tighter constraints on cosmological models, we need to combine with data from the large-scale structure. And here I combine with CMB lensing from ACT and Planck and TCPAO to provide these state-of-the-art constraints on lambda CDM model parameters that you can see as the purple contours on the plot below. And in particular, we provide a 0.5% measurement of the expansion rate of the universe. And as a conclusion, I want to discuss two extensions of the lambda CDM model that are quite simple. And I will start with the lensing anomaly parameter constraints. So these parameter A-lens constrain the deviation of the effect of lensing on the power spectra predicted within the lambda CDM model. And you see on the figure on the right that ACT DR6 data on their own are putting a strong constraint on this parameter, very consistent with lambda CDM expectation of 1. And this is also the case when we combine with larger scale data from WMAP or Planck. And in the same context, we can have a look at curvature constraints on the next slide, where basically curvature is constrained through the effect of lensing on the power spectra from the CMB datasets. And we put a constraints on this particular model using ACT DR6 data. And this is the blue contour that you see on the figure on the left. And there are two conclusions from this plot that ACT DR6 data are very consistent with a flat universe and also very consistent with Pantheon supernovae sample and DESIA 1 BAO data. I just want to precise here that the Planck constraints that are showed here uses legacy PR3 Planck data, and that reanalysis of Planck data using NPipe, namely helipop and CamSpec likelihoods, shows better agreement with flat universe and a length of 1, but this is discussed in more details in the DR6 papers. Next slide. And I now let Herminia Calabrese speak about more DR6 results.
Thank you, Adrian. Okay, so now before giving you more results on cosmological models, we just want to highlight in a different parameter space that the best fit PACT lambda CDM model that Adrian just described gives really good prediction for direct low redshift measurements, which we can then use together with PACT for joint cosmological results. In fact, lambda CDM gives an excellent joint fit to PACT and these datasets, as we show with this plot over here. Now, you've also seen in Adrian's slides that when you bring together this low redshift data with the CMB primary anisotropies, you improve cosmological constraints. And the reason for this is that CMB lensing, BIU measurements, and distance measurements from supernovae help the CMB by breaking geometric degeneracies that are present in CMB-only analysis. Now, this is true for lambda CDM, but it's even more effective in constraints on extended cosmological models, which we are now going to summarize. Okay, so to test our baseline cosmology results, we investigated a large set of cosmological models, both testing foundational assumptions in lambda CDM and setting constraints on its extensions. We look at physics that spans energy scales going from the inflationary epoch to the recombination epoch, all the way to the late time universe. And we do not find any statistically significant departure from lambda CDM, which holds as our preferred cosmological model. We show with 5 benchmark single parameter extensions to lambda CDM here on the right that the results that we find are consistent with standard model predictions, both from cosmology and particle physics, and they are also in agreement with other astrophysical measurements. We set then on these parameters new leading constraints, which improve on current limits, sometimes at the level of tens of percent, and sometimes with larger factors, reaching a factor of 2 to 3 in some cases. We also explore a wide range of models that were constructed with the aim of increasing the value of the Hubble constant or decreasing the amplitude of late time density fluctuations, which we can infer from the CMB. But none of them were favored over lambda CDM by our data. Then in the paper, we discuss what is the specific contribution that is coming to these new measurements from the primary CMB data that we consider. We highlight here complementarity and consistency between the ACT and Planck CMB measurements that we use, and then as well as their complementarity, the improvement that we achieve when we bring them together. In fact, we find that in many cases, the precision of the new measurements of these fundamental physics parameters is completely dominated by the primary CMB contribution. So now, more specifically, where is ACT DR6 adding constraining power for this set of new physics? So to showcase where the data are actually giving us a new lever on constraining cosmological models, we take 3 examples of non-standard cosmologies. So we take a model where there is additional free-streaming dark radiation compared to lambda CDM, setting, for example, the effective number of relativistic species to 3.4. We take a model where 5% of dark matter is composed by axion-light particles with a mass of 10 to the minus 26 electron volt. And then we consider a modified recombination history where we vary the standard scenario by 20% at a redshift of about 1500. And these models are shown in the right in TT, TE, and EE as differences with respect to the baseline lambda CDM best fit. All of these models are allowed by Planck, as you can see by looking at the Planck sensitivity to the CMB power spectra that are here. However, when we add the new ACT DR6 data, all of these models are excluded at high significance. In particular, the TT small scales at multiples above 1700, the TE scales at multiples above 1000, and the whole EE power spectrum contribute to new constraining power for non-standard cosmological models. And now I'm going to hand over to Colin Hill, who will give you some details on specific models.
Great, thanks, Arminia. Okay, so I'm just going to show you a few highlights of our constraints on a variety of extensions to LAMBDA CDM. I want to emphasize that these are just the tip of the iceberg, and I'll point you to the paper for the full battery of constraints that we've derived. So first, let me start with constraints on the primordial perturbations and the properties of inflation. So Adrian has already told you about our constraints on the spectral index NS. The next order correction to look for in terms of the shape of the primordial power spectrum is the running of the spectral index. Our headline constraint is shown here. It's consistent with 0. This is consistent with the predictions of slow roll inflation. I show here a plot of the primordial power spectrum of scalar perturbations, and our headline constraints are shown in the purple band at 95% confidence, and you can see that they're very consistent with the power law predicted from the LAMBDA CDM model. I'll emphasize this is about a 30% improvement over the previous constraints. Turning next to isocurvature perturbations, for the first time, we constrain the possible existence of isocurvature perturbations with ACT data. We look specifically at two possibilities, so-called CDM density isocurvature modes and the neutrino density isocurvature mode. I want to highlight that in particular, we constrain the small scale isocurvature CDM density mode significantly better than Planck, about a factor of 2 better. This is coming from the high L sensitivity of ACT. And then in addition, there was perhaps a hint in Planck of neutrino density isocurvature, not significant in orange here, but it does go away once you add the ACT data. So no evidence of isocurvature perturbations. Let me turn next to particle cosmology. So a major benchmark parameter from the high L CMB is the number of effective relativistic species in the early universe. Here are our results for this parameter and effective. We find a value of 2.86 plus or minus 0.13. So there's no evidence for new light relativistic species that were once in thermal contact with the primordial plasma. If we then fold in BBN data, this tightens up to an error bar of 0.11. The posterior is shown down here in the bottom panel. So the Planck result is in orange, and once you add in the ACT data, you move to the purple posterior. I want to highlight that because the central value goes a bit below 3, this imposes very significant tight constraints on the possible existence of additional particles, additional light particles, which are listed here. We can also do this analysis in a slightly different way, where we assume the existence of the 3 standard model neutrinos and then fit for an excess N effective, delta N effective, that's shown here on the right. And here what you're seeing is the contribution to delta N effective from different types of particles that decoupled at different temperatures from the plasma. I'll highlight that we push these constraints, which are shown in purple, back for some types of particles to eras before the QCD phase transition. For example, for spin 3/2 particles, we find that they had to have decoupled at a temperature higher than 1 GeV. Good, and then lastly, I'll note that we also constrain the existence of the neutrino mass. And like was found for DESI, we get a tight upper limit. Our results are quite similar to what was found in the DESI papers with Planck data. Good, and then in addition to the possible existence of free streaming dark radiation, we also constrain other scenarios, for example, strongly self-interacting dark radiation. The constraints on this scenario are shown here on the right. So the Planck constraints are in orange, our new constraints are in blue and purple. And you can see that we really tighten the upper limit on this possible new component to a value of 0.1. This is about a factor of 3 better than the constraints from Planck, and it really significantly cuts off the possibility of getting a high value of H0 in this scenario. We also do not see evidence for neutrino self-interactions amongst the standard model neutrinos, nor do we see evidence of interactions between a new dark radiation component like this and the dark matter. Okay, then finally, let me turn to a different class of models that modify the dynamics around recombination. So first, let me look at this early dark energy model. The graph here sort of summarizes the theoretical basis of this model, or how we parameterize it. So this is the fractional contribution of this new EDE component to the cosmic energy budget as a function of redshift. So we parameterize the model with the maximum of this curve, FEDE, which is reached at a redshift of ZC. And then the final additional parameter is the initial position on the scalar field potential. So this is a 3-parameter extension of lambda CDM. Those in the field might recall that there was a mild hint of this component in our previous cosmological data release, DR4. With the new DR6 power spectra, we do not see evidence of this component. And we thus find that the mild evidence in DR4 was likely a statistical fluctuation. So the posteriors are shown here on the right, and you can see that the FEDE parameter indeed peaks close to 0. In this multi-parameter extension, one can worry about so-called projection effects in the Bayesian posteriors. So we also do frequentist analyses to check the maximum improvement in the fit that comes from this extension. And in no case do we find a significant improvement. The maximum improvement in chi-squared is 6.6 for the P-act-LB combination, which corresponds to a preference that's less than 2 sigma. So there's no evidence of early dark energy. In addition, we explore possible variation of fundamental constants, the existence of primordial magnetic fields, or deviation of the CMB monopole temperature from its standard value, and we do not see evidence of any of these extensions either. So generalizing, we actually then perform a non-parametric reconstruction of the recombination history. So the graphs here on the right show the ionization fraction as a function of redshift during the recombination epoch. The results using Planck data are shown in orange, and when you add in the ACT data, you tighten the posterior significantly to obtain the purple constraints. In particular, at the higher redshift end of, or beginning of recombination, we really tighten the constraints significantly. And you can see that in all cases, with the ACT data included, they're very consistent with the standard recombination history. So this then translates into a significant restriction of the ability of such models to increase the CMB inferred value of H0, which is shown here in the bottom left. The results with ACT again are in purple for different choices of the BAO data set. And you can see that everything is quite consistent with the lambda CDM value of H0. So then let me wrap up with a look at cosmological concordance. So I've only scratched the surface of the set of models that we studied in this work. I'll point you to the paper for the exhaustive list, but we've considered modifications of the dynamics in the early universe, new forms of energy density, new particles, or interactions between them, as well as modifications of the dynamics at late times, which I didn't have time to talk about. And in no cases did we detect these extensions. This then translates into a lack of shift in the inferred value of H0, which I here compared to the results from Shoes in gray and the latest CCHP results in gold. I'll also note that the results in solid bars here are with ACT plus Planck plus lensing plus BAO, and the dashed ones also fold in type 1a supernova data. Good, and then lastly, looking at S8, we also explored a large variety of scenarios that could potentially reduce the value of S8 inferred from the CMB. In no cases do we detect any of those extensions. They're listed here on the right, including changes to the growth of structure, interactions between dark matter and dark energy, or interactions between dark matter and dark radiation. I'll also note that the lambda CDM results that we have from ACT are actually in statistical agreement already with the latest results from DES and KIDS on S8. Good, so although we don't detect any of these extensions, I'll just emphasize that as a consequence or an implication, we then have significantly tighter bounds on a wide range of beyond standard model scenarios. So I'll point you to the paper to look at those. We're very excited to release the data and to see the constraints that the community derives on a wide range of models as well. So I'll stop there and hand off to Mark Devlin to wrap up.
Well, thanks everybody. That was super exciting. We're going to end with some eye candy here about our nice maps that Sigurd has made. And we want to point out that while this webinar is focused mostly on cosmology, these are legacy millimeter wave surveys of the sky, which have uses for many other things. Of course, all the point sources that you see here. Moving on, we're going to start to answer some questions. Obviously, we're not going to get to them all today, but we'd like to invite people to, we may respond to some of them by email, or you can directly contact the speakers. The first question is for Sigurd, if you could go back to your RGB map of the CMB. Somebody's wondering, did I imagine a blue haze towards the bottom left of the RGB map? And I don't know if we can go back to that slide. It's early on. There you go.
Yeah, maybe you can see it. So a blue haze here would be galactic dust. So this is not a component separated map. So everything that's present at those frequencies is visible. And just like you can see that those nearby galaxies show up in blue because of their dust, the Milky Way itself shows up in blue. Of course, the main band of the Milky Way is not in this frame, but there is some dust elsewhere. So that could be it. Another thing is that the F220 channel is also noisier than the other channels. So even places where there is no dust, there might be a slight blue tint just due to the noise in that channel.
Great, thank you. Okay, the next question, I'm going to go to Thibault. Referring to the TT power spectrum slide, in the temperature, there seem to be some high significant differences between Planck and ACT's measurement at around an L equals 800. Does this persist when constraining to the same sky region?
Yeah, I think I know which point you are referring to. So there is a single data point at L equal 800 that fluctuate high, and I think it's of order like 3 sigma. And given that for this TT power spectrum, we are measuring around like 150 data points, it's expected to have like one outlier at this level. So we computed the probability of this to happen by chance, and it's greater than 20%. So we did not really put too much emphasis on this single data point. I can answer your second question. We also done an extensive study of cross-correlating ACT and MapMap and checking that they are consistent when looking at the same part of the sky, and they are consistent both in temperature and in polarization.
Great, thank you. Okay, next question is for Ide. Are you really using all the TT, TE, EE information up to L of 6500 in the likelihood? If not, what are the effective Lmax values for the 3 spectra that you're using?
So in the ACT baseline likelihood, where we use the multi-frequency data, we go up to an L of 8,500. Above an L of about, 3,000 is where foregrounds start to dominate, especially in temperature. And up to an L of about 6,500, we can still detect a signal from the CMB. So the foreground marginalized likelihood contains data up to 6,500. Above that, the data from 6,500 to 8,500 is purely used to measure the foregrounds in the marginalization procedure. So yes, we do indeed detect, or we do indeed use data for the CMB in all 3 spectra up to 6,500.
Great, thank you. Adrian, can you explain why the contours of the ACT and Planck omega B versus NS are almost orthogonal?
Sure. And this is mainly due to the scales probed by ACT and Planck. Planck is probing larger scales, and in these scales, NS is positively correlated with omega B, because when you increase omega B, you reduce the second to first peak ratio, which can be compensated by an increased tilt of the primordial power spectrum, whereas ACT is dominated by small scales. And then here, basically a larger tilt of the primordial power spectrum is compensated by a smaller omega B to increase seal damping.
Great, thank you. Colin, any idea why the peak of n is shifted below 3 by more than 1 sigma?
Yeah, I think this is referring to N effective. Yeah, so what's happening here is that this is a consequence of the slight lack of excess, or the preference for a lack of excess damping in the high L ACT power spectra. So the dominant channel that lets us constrain N effective is its impact on the damping tail. So if you have more radiation, you damp the spectrum by a little bit more, and if you have less radiation, vice versa. And we see a slightly higher tilt than Planck, which then translates into a value of N effective that's a little bit less than 3. Of course, it's still very consistent with 3. It looks like the 3 neutrinos are there, but this is why it fluctuates a little bit below 3.
All right, thank you. Here's a good one. Thibault, do you have any new constraints on isotropic cosmic birefringence? And just as a follow-up, do you measure any parity violating TB and EB power spectra?
Yeah, so you will be excited to know that we are discussing this in detail in the paper. Of course, for ACT, we still have quite a large systematic error on our angle measurement. We don't have a perfect angle calibration. But if you forget about that, we have this beautiful measurement of EB on TB per spectrum. But then, in terms of interpretation, then you need to add, systematic error on top of it. On most of it goes away. So in total, when you take into account both statistical and systematic error, sorry, we are constant with 0 at 2.5 sigma level. So we are kind of in the gray zone of, we cannot claim a detection by any means. We are not perfectly consistent with 0. But all of the discussion is done in the paper with a lot of caveats due to our uncertainty on our calibration for polarization angle.
Great, thank you. Armenia, do the p-act likelihoods work with the map or spectrum? And if the latter, with the map or the spectrum, and if the latter, do they account for correlations between the ACT and other CMB maps?
We combine a spectrum level, and when we combine with WMAP, we retain the full range of multiples measured by both WMAP and ACT, because there is the high signal to noise from the two experiments is in different regimes, and therefore there is no correlation expected. When we combine with Planck, we actually cut some of the scales in Planck to avoid overlap, and we consider only scales from Planck below 1,000 in temperature and 600 in polarization. In that way, we are minimizing the correlation between the two experiments. We have done some tests, however, in other changing this cut to different multiples or even double counting information, and it has very little impact.
Thank you. Thibault, is there any particular reason for not considering the Planck PR4 likelihoods?
No, actually, we do consider it in a lot of different plots in the paper. We did a very extensive comparison between our result on PR3 and PR4. We just reported on PR3 here. You can see it in the paper. There is some plot that we can show. I mean, if you want to show some plot, but we are cross-correlating both with NPipe and with legacy. So this is, for example, a comparison of ACT and Planck on the same patch of the sky. And we are comparing ACT cross Planck power spectrum for both with Planck cross Planck for both legacy and NPipe. We do find a slight preference for legacy, but it's by no means very significant. But it's in particular driven by the 100 GHz measurement of the T power spectrum in NPipe that is a bit more discrepant with our measurement than the legacy one is. At this stage, it's very difficult to say something very definitive on this. We have very consistent EE measurement both with NPipe and with legacy. It's only there's a single T power spectrum where we are more consistent with legacies than with NPipe.
And as long as I have you, Thibault, do you have results compared with SPT?
No, we did not, but we are really excited to do this in the future, in particular where SPT is going to publish, the spectra that will cover like a large fraction of the sky. There will be so much synergy between the two experiments, so much cross-correlation that we can do, that we'll be able to do. So we are super excited to collaborate with SPT in the future.
Excellent, thank you. Okay, we're almost done. Adrian, can you show the ACT S8?
Sure. You can go to slide 101 or something like that, which shows the S8 omega m constraints from Planck ACT and the P ACT combo that we have, and we see like constraints that are really consistent with what Planck previously found with this combo, and also with the ACT DR6 lensing constraints, if we compare to kids and deaths on this plot.
Excellent. Well, at this point, we have reached the hour, and we really appreciate the many people who showed up, and also want to reiterate the huge effort that was put in here by many people on the ACT collaboration, and of course our consistent support from the National Science Foundation to get all of this done, along with many other supporters of the of ACT and our Chilean colleagues for allowing us to operate in Chile for so many years. And with that, we're going to conclude our webinar. Again, if you have any other further questions, please feel free to contact the speakers or anybody else on ACT. And please go to our website to go and get the access to the papers and any updated information. Again, thank you very much for attending.